So what we have done last time, we studied the fields of the electric dipole radiation with a oscillating dipole moment as a source. Then we find that the emitted power per salt angle is proportional to magnitude of the electric dipole moment, and this distribution is as a dipole sine square theta. So basically, if you have an oscillating source, this kind of distribution, along the direction of the electric dipole moment, there is no radiation, and the maximum radiation is along the 90 degrees to the electric dipole moment. And if you integrate this through the salt angle, you can find that the total radiation, total power, is again proportional to the square of the electric dipole moment. So then we start to study the other kind of radiations, magnetic dipole moment radiation and the quadrupole moment, electric quadrupole moment radiations. We will study these things today. So what we have done, we took the vector potential, which is coming from the solutions of the non-homogeneous wave equation under the Lorentz conditions. So we have the source and the Green's function here, and we use that the expansion of this Green's function in terms of spherical harmonics and Bessel functions. So we choose the particular case L equal to 1, and we use that the asymptotic forms of the Bessel functions when we are at far field zone, kx is greater than 1, and the source is smaller to the with respect to the wavelength. So kx prime actually is the x prime or magnitude of the source divided by wavelength. So that should be small, means that our source is, the source of the radiation is smaller with respect to the emitted wavelength of the radiation. So anyway, we derive the following formula. Today we will play with this vector potential. We will try to interpret this integral in terms of the magnetic dipole moment and the electric quadrupole moment tensor. And if we have a time, we will do examples. So let us start to let us try to take this integral. Put this integral something we know, quantities which we know. So if you take the n dot x prime j, you can write this in the following form. So let me write it in terms of first the cross product. So consider the following cross product: x prime cross current density cross product with n hat. So this is the double cross product. That is equal to take this to the other side with the negative side and use that the double cross product rule. You will get minus n dot current density along x prime. So if you pick up the term n dot x prime times current density, which is our integrand, you can write this in terms of the other terms in the following form. So let us write this form in the following form: 1/2 n dot x prime along current density minus n dot j of x prime along x prime plus 1 over 2 x prime cross current density cross n hat. So indeed, using this identity, the above is the same. So let us look at very quickly. So if you take this to the here, you will have minus 1 over 2. Everything will be in 1 over 2 parentheses. So 1 over 2's will be cancelled. So that will be minus n dot x prime j, which is this term. And the other term was, what is the other term? Plus, so sorry about that. If you take this to the here, that will be minus 1 over 2, and everything will be in 1 over 2 parentheses. So n dot x prime j is here. I am sorry. Yes. And if you take the other term to the other side, that will be positive, and that is x cross j cross n. That is correct. Okay, that's correct. Yes, that's correct. What is wrong here? This should be plus. This should be plus. So if you take this term to the other side, that will be negative. Okay, that's okay. So instead of n dot x prime along j, the integrand of this term, I can write 1 over 2 of this stuff and the other stuff. So the property of this following. So if you replace the x prime and j, you will get negative of the original term. That is anti-symmetric. But if you replace that the x prime and j, this will be x prime, that should be j, and this will be j, that will be x prime, this will be the symmetric part. This anti-symmetric and symmetric part could be interpreted as it will be interpreted in terms of magnetic dipole moment and the electric quadrupole moment tensor. So let us wait and see. So let us concentrate this term first. Okay. So are you clear that this? Yeah, that is clear. So now we will try to investigate the first that term, which is the anti-symmetric part, if we replace the x prime and j, and the other part is the symmetric part. So we will investigate in 2 steps. And as a whole, this is our integrand. So what we see very quickly here, x prime current density. This is something you know from the past. That is the definition of what? You are saying automatically one term as a definition, x cross j. What is the x cross j? J is the current density, x prime is the location. So if you have something here, a current density, and if you say this is x prime, x cross j, so you know this. Magnetization. So you know this. So magnetization is the density of the magnetic dipole moment. If you integrate this through the volume, you will obtain that the magnetic dipole moment. So it automatically comes the definition of the magnetization. Magnetization. And actually, it includes the 1 over 2. This includes the 1 over 2. So if you integrate this through the volume, magnetic dipole moment, M will be 1 over 2 times magnetization through the volume. That is magnetic dipole moment. So since this part inside the integral, we will automatically see that the vector potential in terms of magnetic dipole moment. So let us take this term, plug inside, and study the first part, which I said a symmetric part later, okay? So take this part as a part of the integral and write the vector potential. Actually, that vector potential will be related to the vector potential due to the magnetic dipole radiation. So if you take this part and plug inside the vector potential, you will get the following thing. mu0 over 4 pi e to the ik r over r, 1 over r minus ik, and 1 over 2 x prime cross current density integrated d cube x prime, and cross product with n. Cross product with n. So this is the first term. First term of the first part of the integral, 1 over 2 x prime cross j. That term should be integrated. Then cross product with n. Basically, this whole thing is the magnetic dipole moment, M. Then the vector potential could be written in the following form. A will be ik, take the ik parenthesis, mu0 over 4 pi, switch the order, n cross m, e to the ikr over r, 1 minus 1 over ikr. What I did here, I took the ik parenthesis, then that becomes negative, but I changed the cross product. Instead of m cross n, n cross m. I have the spherical wave part, e to the ikr over r, and some coefficients here. That is written in that form. So now we have the some current, let's say, in the loop, oscillating at frequency omega t. It has some magnetic dipole moment, m, and we can calculate the vector potential at any point. Since I know that the vector potential, I can calculate the electric field and magnetic field. So how I can do? The simplest, think about the electric field. Electric field is what? Minus gradient of the scalar potential minus del A over del T. We are not considering any scalar potential here because the current is what? The current density is what? Neutral. Net charge in the current is 0. If you have a wire, think about the wire. The current at any volume element in the wire should be neutral. Okay, there is no net excess charges. So therefore, we don't think about anything about the scalar potential. So that is 0. And what I can write instead of del over del T, I know that my source is oscillating some frequency omega, and magnetic dipole moment is oscillating some frequency. And if you want to write this in terms of time dependent, all you have to do multiply by I omega t. So this is position and time dependent. And here you have to write the derivative of this in general. And you know that del over del t will be replaced by minus I omega. So basically the electric field is nothing but, is very simply, is plus I omega A. And if you do the unit arrangements, you will get the following. I and I is minus, so omega k over 4 pi mu 0 n cross m 1 minus 1 over IKR, and spherical wave term e to the IKR over r. So you can put the time dependent part or not, so it's okay. So this is the space part of the electric field. So if you multiply this by k and k, this becomes k square over k. And what is omega over k? Omega over k, speed of light, that is equal to 1 over square root of mu 0 epsilon 0. One of the mu zeros will be cancelled. That will be square root of mu 0 epsilon 0. That will be the impedance of the free space. So basically this will be all together, this will be minus S0 over 4 pi times k square, and the rest will be n cross m 1 minus 1 over IKR e to the IKR over r. This will be the electric field. Now I am going to make some little comparison with the last time we did. Last time we calculated that the fields of the electric dipole moment. So if you look at your notes, you will find something. So look, what was the H for the electric dipole radiation? H was equal to C k square over 4 pi e to the IKR over r 1 minus 1 over IKR n cross p. That was, if you look at the notes, you have this derivation. This is the magnetic field of the electric dipole radiation. So if you make a comparison with the electric field of the magnetic dipole radiation and magnetic field of the electric dipole radiation, what is the similarity? So I would write this again. E is equal to minus S0 4 pi e to the IKR over r 1 minus 1 over IKR n cross m. So the functional form exactly the same. Magnetic dipole moment and the electric dipole moment is replaced. Okay, so basically from up to down, P goes to M over C. Basically electric dipole moment is replaced by the magnetic dipole moment. So there is a very nice symmetry between the H field of the electric dipole radiation and the electric field of the magnetic dipole radiation. And if you want to calculate the next thing is tough. If you want to calculate the B or H, what is the H? H is mu 0 times B, and it is mu 0 curl of E. So you have to take the curl of this. So that is long, but I did the same thing. So if you remember from the last time, taking the curl of H, I calculate the electric field. Almost all hour I spent that derivation. Since the functional form is the same, I can write the result much more easily, so I will just write it, okay? That is the exact same procedure which we did 2 days ago in the first hour. So you will come to the point for the H as following. So if you take the curl of E, you will obtain 1 over 4 pi k square n cross m cross n hat e to the ikr over r plus 3n n hat dot m minus m and multiplied with 1 over r cube minus ik over r square e to the ikr. And the electric field for the same thing is what? The same electric dipole moment. So you have the same structure, but instead of M, you have P times C. So that is going as N cross P cross N hat e to the ikr over r plus it's exactly the same form. So I am not writing again. This is in your notes. So what is changed? For the magnetic dipole radiation, instead of H, you have E, and for electric dipole moment radiation, you have the opposite of this. So if you have a electric magnetic dipole, let's say you have some circular current loop oscillating some frequency. What is the magnetic dipole moment? If the radius is r, that is nothing but the current times p a square. The current times the area, that is the magnetic dipole moment. And if you look at the far field zone, which term is dominated in the far field zone? So maybe I should do what I did in the last time again in order to remind you what was happened. In the far field zone, which term is dominated? So this term is dropped, and you will have the electric field as minus S0 4 pi e to the kr over r n cross n when kr is greater than 1. And for this one, what is the h? H is 1 over 4 pi k square n cross m cross n e to the ik over r. This is the structure in the far field zone. What is the relation between the E and H? So H is m cross n of this. So you will find that the E is proportional to the H cross N. The proportionality constant in that case should be the 1 over impedance if you do carefully, okay? So that is the same thing, same words we said in the last time. In the far field zone, electric field, magnetic field, and normal propagation are mutually orthogonal to each other, okay? Exactly the same. What has changed? Instead of P, you have N. And if you want to study that the magnetic power emitted for magnetic dipole moment radiation per unit time, you will obtain different coefficients, but the structure will be what? In that case, this times sine square theta. Okay, like electric dipole moment radiation. So that will be a dipolar radiation. If you go to that near zone, which term will be the dominated? This term goes as a 1 over r cube. So 1 over r is not important, 1 over r square is not important in the near zone. Only important term is what? H, when Kr is small, then the important term is 3 n hat n dot m minus n over r cube. So you have 1 over 4 pi also. And electric field in the near zone goes as a 1 over r square. It's not important. So basically, you will obtain that the only dominated component is a H field in the near zone. The electric field is not important. But if you look at that, so that will be the H field in the near zone. And if what we have done last time, we did the same thing for the electric dipole radiation. And if you go to the near zone of the electric dipole radiation, the dominated term was the electric field. And indeed, that term over there will be dominated. So if you have a magnetic dipole radiation in the far field, the source of the radiation is the magnetic dipole moment, and E, H, and mutually orthogonal to each other. Propagation, electric field, and magnetic field are mutually orthogonal to each other. Amplitude of the fields goes as a 1 over r. They are spherical waves. And if you come to the near zone, close to the source, the dominated term is 1 over r cube. And if you look at this, you will get exactly the field of the static magnetic dipole. So which you saw in the first part of the course. And the electric field is not important in the near zone because it goes as a 1 over r square. So you have some structure of the static field lines when you come to the close to the source, which is the H. And if you do the same study for the electric dipole radiation and for the near static zone, the dominated terms are the electric field lines. Okay, what has changed? E and H and E are replaced, okay, for the electric dipole radiation and magnetic dipole radiation. Only thing you have to calculate that what is the magnetic dipole moment for the magnetic dipole radiation. The typical example is the circularly oscillating current loop. And the calculation of the magnetic dipole moment is very easy. For the electric dipole radiation, you have to know that the electric dipole moment of the system. So the next thing, what is the rest of the integral in the original definition. So do you have any question in regarding that the electric dipole and magnetic dipole radiation? If you have two sources, that configuration is difficult. So if we have one magnetic dipole moment in one direction, the other is other direction, then you have to find that the fields at any point, then you have to calculate using the fields, you have to calculate that the total field, electric or magnetic field, and then you should calculate that the power emitted per solid angle using the total electric field and magnetic field. But if you have a single source oscillating single frequency, the things are easy. Now, I am going to continue the other part of the integral. And if I have a time, I will do an application today. So, where we stop? Here is our integral. So let me write this again. The vector potential mu0 over 4 pi spherical wave term e to the ik over r 1 over r minus ik, the current density dot n dot x prime d cube x prime. And for that integrand, I wrote that the n dot x prime along current density is equal to 1 over 2 n dot x prime along current density plus n dot j along x prime plus 1 over 2 x prime current density cross n. So I studied this part. Okay, now let us study that part, second part. So for the second part, I will use the indices which make the calculation easy. So first multiply x and divide by x magnitude. You will obtain for the second part of the integral to the following: 2x. Let me just write the integrand. Yes, I am doing this. Multiply by x, divide by x. You will have x dot x prime along current density plus x dot current density along x prime. So this is the second part. I multiply with x and divide by x. Now do the following for the one particular component. Say alpha. Alpha could be x, y, z, or 1, 2, 3. So actually alpha is 1, 2, 3. So for particular component. So for particular component, consider the following divergence. Divergence with respect to the prime, x prime, of x dot x prime alpha j. So consider this. So I am trying to evaluate this integrand, and you will see that we will do very easily. Consider this: divergence of a scalar times the vector. What is the divergence of scalar times a vector? Scalar x dot x prime and the alpha component of x prime times divergence of vector, and as you know that from the continuity equation, that should be related with the charge density, plus a vector dot product with the gradient of the scalar. Gradient of the scalar. X dot x prime x prime alpha. So you will see that one term will give this. So let us say consider, just consider. So divergence of J, you know that that is I omega charge density from the continuity equation. That is equal to minus del rho, del dot J is equal to minus del rho over del T, and del over del T minus I omega, that is okay. Only term we will play the second part. So I'll do the following. I will write this in terms of indices. So basically, instead of if you have A dot B, a scalar product, I will write AI BI, I 1 to 3. Okay, if you have a scalar product, but I will not write the summation. Okay, I will just show you AI BI. Okay, in order to not use the space more. So that will be equivalent to that. So for that particular derivation, this is okay. So we will do this together. We have x dot x prime alpha e omega charge density plus. How many scalar products here? One scalar product here and the other here. So for J times gradient, dot product gradient, I will write J gamma del gamma with respect to the prime. You have a summation here, okay? If you have two indices, the same, think about a summation, and gamma goes 1 to 3, okay? This is the scalar product J dot gradient, and here what you have, x dot x prime, then use a different indices for that dot product. So I'll use x beta, x beta prime, and I have x prime alpha. Is it clear to everybody? This is the first scalar product. This is the second scalar product. Beta is 1, 2, 3. It is sum. Okay, if the two indices are the same, you just sum it. So let me continue one more step here. The first part is the same. J gamma, and how is the derivative? This derivative will act to this one, then it will act to the second one. This is not prime, this is prime. This derivative doesn't see x. Okay, you have two things there. So one is the x beta, leave the x beta out for all derivatives, then j gamma, and this will be acted first to the beta, that will be del prime gamma x prime beta, and left with x prime alpha. The other term will be what? Let me take the j gamma and x beta outside the parentheses, add this del prime to the x prime beta, then you have x prime alpha left over, and what will be the other derivative? That will be x prime beta del prime gamma x prime alpha. Is it okay to everybody? So I take the derivative with respect to the first this one, then take the derivative with respect to the other one. Okay? Now, what is delta gamma x beta prime? Delta prime gamma x beta prime. This is xyz, this is xyz. That is del over del x, del over del y, del over del z. This is xyz, x prime, yz prime. If gamma and beta are equal to each other, you will get 1. Otherwise, you will get 0. So the representation mathematically is chronicle delta gamma beta. If gamma and beta are equal to each other, you will obtain 1, otherwise 0. Same thing is here. You have chronicle delta gamma alpha you have. Okay, for the other term. So let us try to go one more step. I think write the things again here. X dot x prime alpha I omega rho x prime So can I erase this term and the below one? Everybody copy it. So erase this one. So you write one more step. You write one more step. So let you write again. X dot x prime alpha I omega rho x prime that. Now tell me that how many indices beta, gamma, alpha. If you sum gamma indices, what will be the j? If you sum gamma indices with chronicle delta, what you are going to obtain? J gamma sum with chronicle delta gamma beta, and gamma is the dummy index. What will be the leftover? J beta. J beta. This will be J beta, and this is X beta. Therefore, this should be X dot J. So basically, first use this dummy summation. This becomes J beta, and you have X beta, and you will obtain for the you have the J beta, X beta eventually, and that should be X dot J along X prime alpha. Is it clear to anyone? Everyone here? So what about the other one? Chronicle delta gamma alpha. You have gamma here, and you have a gamma here. If you sum the J gamma with chronicle delta gamma alpha, J becomes J alpha, and you have J alpha, but you have X beta prime. That makes X dot X prime J alpha. So the other term will be X dot X prime J alpha. Okay. Now, let me go one more step before we break. Do you have any question here? Okay, so let me go one more step. First, is there any similarity between this term and that term, last two terms? Look at this. That term and that term which we want to look at. We have x dot x prime. Instead of J current density, we have alpha component. Alpha is x, y, z. And for the other term, x dot J we have instead of x prime vector, we have x, y prime, x prime, y prime, z prime. So this is in terms of component wise, this is the vector, but they are the same as a form. So I want to write the result very quickly now. If you multiply whole term d cube x prime, and integrate through the volume, so this is not a good presentation here, but it is enough to understand. If you multiply side by side with the volume element, and if you integrate it, what you are going to obtain? From the divergence theorem, this goes to the what? Surface integral. Okay? And what will be the elements of this? X dot x prime alpha component, J dot m prime, integrated the surface. When the surface goes to infinity, we don't have any source because the sources are localized. Current densities and whatever is localized. So when the surface goes to infinity, from the divergence theorem, this drops to the surface integral, and this will be 0, and therefore this should be 0. Okay? So basically, if you do this for each alpha component, x, y, z, component by component, you will obtain the following integral, and your result will be what? So let me write in the above term. So that will be mu 0 over 4 pi e to the ik r over r 1 over r minus ik. So what you are going to obtain? So I am trying to calculate this integrand. I calculated for the magnetic dipole moment term and the leftover that term, and instead of that, what I am going to obtain? So what will be the volume integral of this? This should be related with this term, because if you integrate through the volume of this term, you will obtain the following result. Your result should be minus I omega over 2. You have I omega here minus, because this comes to the other side. We have a 1 over 2 factor there. And then instead of x, if you multiply everything side by side with x, that becomes an unit vector, and your result will be the charge density x prime dot x prime and dot x prime integrated through the volume. So let me erase this because I want to clarify everything again for you. So first of all, we consider this term and we express this in terms of this. For alpha 1 to 3, you will obtain this term is exactly this whole term. If you integrate both sides through the same volume, of course, from the divergence theorem, the first term drops, and you obtain this instead of this term, the symmetric part, x dot x prime alpha I omega rho. If you divide the things to the x, 2x here, then x will be an unit vector. That will be divided by 2. And this term goes to the other side is minus, and you obtain that. So in the next hour, I will play this vector potential, and I will express this in terms of the electric quadrupole moments. Do you have a question here in the derivation part? So if you go over this derivation by yourself, you can easily do. So it's very straightforward. I show you the trick of the indices. That's all.